A priest watches a chandelier swing during a sermon and accidentally invents the future. It's 1581. The Cathedral of Pisa is still standing. A man named Galileo Galilei sits in the pews, bored, watching a chandelier sway above him. He has nothing to measure time with except his own pulse. His heartbeat becomes a clock, and in that moment, without knowing it, he's about to change how humanity keeps time forever. What Galileo didn't know yet was that the pendulum he was watching obeyed a law, a hidden rule. It didn't care how far it swung. It didn't care how heavy it was. The time it took to complete one arc, then swing back, remained almost perfectly constant. Almost. This property, this stubborn, reliable rhythm, would become the heartbeat of civilization. But Galileo couldn't prove it yet. Not that day. He'd need years, decades, really, to understand what he'd seen. And he'd never live to see a clock built on this principle. That's the cruel gap between observation and invention. Seeing the pattern and knowing how to use it are two entirely different things. Fast forward to the 1650s. Christiaan Huygens, a Dutch mathematician and astronomer, is working on something Galileo never finished. He's building the first pendulum clock. He understands the mathematics now. The period of a pendulum, the time it takes to swing and return, depends on only one thing: the length of the string. Make the string longer, the swing takes more time. Make it shorter, it quickens. Everything else is noise. Huygens didn't know it, but he was solving one of humanity's oldest problems. For thousands of years, we'd measured time by the sun's shadow, by the stars, by the drip of water through holes. All of it was imprecise. All of it drifted. But here, in a simple rod and weight, was something that could tick with mechanical certainty, over and over. Reliable, predictable. The first pendulum clocks weren't perfect. They lost or gained minutes over days, but they were close enough to change everything. Suddenly, time could be divided into smaller and smaller pieces. Seconds, fractions of seconds. The world became measurable in ways it never had been before. But there's something deeper here, something that most people miss. The pendulum wasn't just a tool, it was a window into physics itself. Every swing proved that the universe wasn't random. It obeyed rules, laws that could be written down, measured, predicted. A pendulum swings the same way today as it did 300 years ago. That consistency, that's not luck. That's the universe whispering its secrets. By the 1700s, pendulum clocks had spread across Europe. They hung in churches, in town halls, in the homes of wealthy merchants. For the first time, entire cities could synchronize. A meeting could be scheduled for 3 o'clock and everyone would arrive at the same moment. Before this, 3 o'clock meant something different in every town. Time was local. Now it was becoming universal. The Industrial Revolution couldn't have happened without it. Factories needed synchronized workers. Trains needed precise schedules. Telegraph operators needed to coordinate across continents. The pendulum made all of it possible. It was the invisible spine of modernity. Yet even as pendulum clocks became ubiquitous, scientists were learning something strange about them. Temperature mattered. A pendulum that's cold swings slightly faster than one that's hot. The metal expands and contracts. The air around it becomes denser or thinner, tiny variations. But in a precise instrument, tiny becomes everything. Engineers obsessed over this. They built pendulums from special metals that barely expanded. They housed them in sealed boxes. They compensated mathematically for variations they couldn't prevent. It became an arms race of precision, and it was necessary. Because by then, humanity had realized something. Time itself was becoming currency. You couldn't afford to lose seconds. The pendulum also taught physicists something profound about motion itself. When you swing a pendulum, it trades energy back and forth. At the bottom, it's moving fastest, kinetic energy at its peak. At the top, it pauses for a moment, potential energy at its peak. This exchange, this dance between two forms of energy, happens identically every single swing. It's the heartbeat of physics. This principle, conservation of energy, became one of the pillars of modern science. It applies to everything: planets orbiting stars, atoms vibrating in molecules, light waves traveling through space. The pendulum was a teacher, a simple, elegant lesson in how the universe actually works. By the 20th century, pendulum clocks had been surpassed. Quartz clocks were more accurate. Atomic clocks were more accurate still. The pendulum was obsolete as a timekeeping device, but it never stopped being important, because it remains the simplest, most intuitive example of a physical system that behaves predictably. Students still learn from it. Scientists still reference it. There's something almost poetic about that. A chandelier in a cathedral, a priest's sermon fading into background noise, a young man with nothing but his pulse and his curiosity. In that moment, Galileo was watching the future being born. He didn't know it, but the universe was showing him one of its deepest secrets, that chaos and randomness can hide an underlying order, that beneath the noise there's rhythm. The pendulum's swing isn't just a measurement of time, it's a measurement of reality itself. Every oscillation is a promise that the world obeys rules, that we can understand it, that we can predict it. And in a universe that often feels chaotic, that's perhaps the most beautiful secret a simple object can hold. Subscribe to keep discovering the hidden physics hiding in plain sight, the science behind the ordinary that changes everything.